Hey everyone, I'm going to pick up where I left off last Monday. I spent last Monday telling you about asymptotic analysis and big O notation. We took a detour on Wednesday to talk about hash tables, so you'd be ready for homework 6. Now I'm going to finish up talking about asymptotic analysis and also talk about how to analyze algorithms and give some basic examples of algorithm analysis. So first of all, asymptotic analysis, I've taught you big O notation. There is another notation that is essentially the reverse of big O notation called big omega notation. And so big omega of f of n for some function f is a set of functions just like big O is. So here in the box is another definition that you should memorize. It's very similar to the definition you already saw last Monday. There's just one difference. If you compare this with the definition of big O, in big O, that last expression had a less than or equal to sign. So big O was the set of all functions that are less than or equal to f of n when you multiply it by a big enough constant. Big omega is the set of all functions that are bigger than f of n when you multiply it by a small enough constant. So another way to think of this is that omega is the reverse of big O. And what I mean by that is that if you have a function that's in big O of another function, then the second function is in big omega of the first function. And so, for instance, we can say that the function 2 of n is in big omega of n. And the reason we can say that is because we know that n is in big omega of 2n. So the function 2n grows at least as quickly as n asymptotically. We can also say that n squared is in big omega of n. Because n is in big O, n is in big O of n squared. So, big omega is saying here that n squared grows at least as asymptotically quickly as n does. In this case, n squared actually grows more asymptotically fast than n does. N squared asymptotically dominates n. And so the big omega notation tells us that if this is our running time here, then our running time is at least this slow, but maybe slower. And so n squared is in big omega of n for the same reason that n is in big O of n squared. Or you could say that n squared is in big omega of 3n squared plus n log n. And just like with big O notation, it's the dominating term that really matters. So when you see an expression like big omega of 3n squared plus n log n, the part that should catch your eye is the n squared term, because that's what dominates. The n log n doesn't grow as fast as n squared, so you don't worry about it. You just focus on the n squared, and you don't worry about the 3 because constant factors don't matter in big O or big omega notation. So the difference between big omega and big O is that big omega gives us a lower bound on a function. Just as big O gives us an upper bound. Or to put it another way, big O notation says your algorithm is at least this good in terms of running time or memory use or some other feature. Big omega says your algorithm is at least this bad. So one thing you might recall that I said last Monday is that big O notation can be misleading, because if an algorithm's running time is big O of n to the 8th power, that doesn't mean that the running time isn't also in big O of n. So if I say big O of n to the 8th, that's an upper bound. It says it's at least as good as n to the 8th, but it might be much, much better than that. You don't really know. Big O notation doesn't tell you. So we have another notation that does tell you, that you can use when you want to specify that you really tightly know the running time of an algorithm. And that's called big theta notation. Which you can use to precisely specify the function's asymptotic behavior. And so here's the formal definition of big theta notation. Theta of a function f of n is the set of all functions that are in both big O of f of n and big omega of f of n. Once again, that's a formal definition that you should memorize, so I've put it in a big box. And by the way, I could have written this a much shorter way. A perfectly equivalent definition is to say big O of f of n equals big O of f of n intersect big omega of f of n. Because it's just an intersection of two sets of functions, though it's a little bit more obscure what it means when I write it that way. So, if I say that a function, or if I say that your algorithm's running time is in big theta of n squared, that means I'm giving you a precise bound on how your algorithm's running time behaves in the limit as the input size goes to infinity. So I'm saying both, it's, in the worst case, it's not going to be slower than n squared, but I'm also saying in the worst case, it's not going to be faster than n squared. And so you might ask yourself, well, how can a function be bounded between n squared and n squared? What does this definition mean? Well, let's draw a function then. The horizontal axis is going to be n, the input size. And I'm going to draw a function which I claim is in big O of n, even though it's not entirely obvious until you look all the way to infinity. But here's the function. So I'm going to call that t of n. And maybe that's the running time of some really weird algorithm as a function of the input size. It's very unusual to have an algorithm that's not monotonically increasing with the input size, but they do happen in weird places like number theory. So if I say that this is in big O of n, I'm saying that I can draw a linear line through the origin, and that function is below it. I'm also saying I can draw a linear line through the origin, and that function is above it. And the difference between those two linear lines is that I have different constants, the constants c and d, that I used in the definition of big O and big omega. So in other words, to show that this function is in big O of n, I need to draw the right line with a big enough slope that that function will always stay underneath that line as n goes to infinity. And so maybe this is c times f of n, where c might be 10. So that line is 10n. And I draw a different line to show the big omega bound. So this will also be a linear function. And this linear function gives us the constant d, the same constant d I used in the definition of big omega, times our function. And maybe d is 2. And our function is n. And so, what I'm saying is, these two lines form a cone going off to infinity. That wavy line in the middle, as long as that wavy line always stays between 2n and 10n as n goes to infinity, then we can say that that function is in big theta of n. So t of n is in big theta of n because it stays between those two lines as you go off to infinity. And of course, the lines you need to pick different constants, one for the lower bound, one for the upper bound. Are there any questions about this so far? So a few other useful bits of information. One is that theta is symmetric. And what I mean by that is if you have a function, f of n, that's in theta of some other function, g of n, then it works both ways. G of n is in theta of f of n. So we call that symmetry. For example, n cubed is in big theta of 3n cubed minus n squared, and 3n cubed minus n squared is in theta of n cubed. If one is true, then the other one has to be true as well. Just like big O notation, we usually use big theta notation like this, meaning we usually try to put something really simple inside the parentheses when we use big theta, the simplest thing we can think of that will describe the function. We don't usually use this notation when we use big theta, but you can. This is perfectly mathematically legal. It's just not expressing things in the simplest way possible. And usually you use big theta notation to communicate something about the running time of an algorithm, so usually you use the simplest thing possible. So big theta notation is not potentially misleading in the way that big O notation can be, where if I say that an algorithm is in big O of n to the 8th power, that doesn't necessarily mean it's slow. But if I say an algorithm's worst case running time is in big theta of n to the 8th power, then I'm saying it's necessarily slow. There are, I should say, functions that are not in big theta of anything simple. Most of the algorithms you ever want to analyze, there will be a pretty simple big theta expression for their worst case running time, but there are exceptions to that. Well, there are exceptions in functions, not necessarily in algorithm analysis. But I want you to consider, for instance, the function f of n equals n 1 plus sine n. This is an example of a function that's kind of mathematically weird in its asymptotics, because what this function does, if you graph it, is, let's draw a line here. This is not the function, but this is going to tell us something about the function. The function f of n equals n times 1 plus sine n has the behavior that it keeps oscillating back and forth between 0 and a linear line. And it will revisit 0 an infinite number of times. So this is an example of a function that isn't really asymptotically going towards some normal simple function. You can say that this function f of n is in big O of n because it never gets bigger than n. And you can say that this function is in big omega of 0, which honestly doesn't tell you very much at all. But you can't say that it's in big theta of n. You can't say it's in big theta of 0. You can't say that it's in big theta of anything simpler than itself. You could say, if you want, that f of n is in big theta of 2n 1 plus sine n. But that's not giving us any useful information or simplification. So you can use big theta notation with this function, but not in a meaningful way that communicates anything useful. So this is an example of a function that's just not in big theta of something simple. It's definitely not in theta n, because it revisits 0 an infinite number of times. And it's definitely not in big theta of 0 either. Question in the back, was there? There's no algorithm that acts like this. So this is just a purely mathematical statement right now. But what you do have often in practice is not algorithms that act like this, but algorithms where you actually don't know for sure exactly how fast they are. Like, you know that you can prove an upper bound, but you don't know if that's the tightest upper bound for that particular algorithm. It might be that a smarter person with a better analysis could prove a better bound. And so there are many interesting algorithms in the research literature where we don't know what their fastest running time is. Any other questions about this? Yeah. That f of n what? F of n. Oh, I'm sorry. I forgot to put the cross through here. Is that what you're asking about? All right, sorry about that. And thank you. So that's everything I have to say about asymptotics proper. What I want to talk about next is analyzing some algorithms. Actually, do I want to do it on this page? Let's do it here. Something you will probably have to do a lot if you take the upper div courses is look at algorithms and figure out how fast they run in big O, or better yet, big theta notation. So let's look at some algorithms and think about how to do this. I'm going to start with a simple problem. You are given a set of p points. These could be points in the plane or points in three-dimensional space. It doesn't really matter which one. What you want is to find the pair of points among those endpoints that are closest to each other. And I'll give you an algorithm now for solving this problem. It's kind of the obvious algorithm. You look at every pair of points, you compute the distance between those 2 points, and you figure out which those distances is smallest. So pretty obvious algorithm. How fast does it run? Well, we're looking at every pair of points. How many pairs of points are there? That many. P times p minus 1 divided by 2. That's how many different pairs there can be of distinct points. And each pair is going to take a constant amount of time to examine it to compute the distance between those 2 points. So, multiply that many pairs by constant time to process each pair, and it should come as no surprise that the total running time must be in theta of p squared. And to reinforce the point, I've written out the code here that does this. Don't try to copy all the code down now. It'll be in the lecture notes. But just look at what's going on here. The most important thing to notice is that this is an algorithm that pretty much exposes its own running time in a really obvious way because you have 2 loops. You've got the outer loop here, and you've got the inner loop here. And the outer loop iterates once for each point. The inner loop, how often does it iterate? Well, the inner loop iterates at most once for each point. So in the worst case, this algorithm is going to take big O of p squared time. That doesn't tell us the big omega, though. But you'll notice that the loop bound it's not running exactly p times. It's always starting the second index at the first index plus 1. So sometimes the inner loop will run many times. Sometimes the inner loop will run just a few times. And the reason for that is we don't want to check every pair twice, so we only check pairs where the second index is bigger than the first index. So that means that if you're looking for a lower bound, you have to realize, okay, this is not going to run order p times every time the outer loop runs, but it will run p over 2 iterations for at least half of the iterations of the outer loop. So there are p over 2 iterations of the outer loop for which the inner loop will also iterate p over 2 times. That's one way to think about it. A second way to think about it is that we know that since this iterates on all the indices bigger than I, that it's going to iterate on average about p over 2 times. The first time you go through the outer loop, the inner loop will iterate p minus 1 times, because you're checking index 0 against every other index. The last time you go through the outer loop, the inner loop will iterate 0 times, but the average will be about p over 2. So p times p over 2 gives us p squared over 2 is roughly how many iterations we get, and so multiplying those, again, it's pretty clear that this algorithm takes theta of p squared time. Any questions about that? So one reason I showed you this example, though, is because now that we've seen that it's very common that with code, you can just look at the loops and you can figure out the running time from the loops. Nevertheless, that can be misleading. Let me show you a piece of code that also has 2 loops just like this, an outer loop that could run n times, an inner loop that could run n times, and yet the overall running time is not n squared. And that example will be one that you're somewhat familiar with, because the problem that we're trying to solve is a problem you solved in homework number 3. And that is smooshing an array. Remember in homework 3 you wrote a method called smoosh that goes through an array of ints and removes all the duplicates, or all the adjacent duplicates from the array. So, algorithm number 2, I don't know how you solved it, but here's how I solve it, is with this code here. I've left out the bit at the end that fills in the minus 1s at the end of the array. But what I've got here is my loop for walking through an array, and as we walk from left to right through the array, we're looking for entries that are identical to the next entry, and when we find them, we copy them back to, when we find ones that are different, we copy them back. When we find ones that are the same, we ignore them. So you have an index I, and you have another index j, and the point is that I is going to be wherever I'm copying numbers to. J is going to be wherever I'm copying numbers from. So as I go through an array, I is going to be pointing at the current thing that's not a duplicate, and J is going to be pointing to duplicate copies of that same number. And when I find a number that's not a duplicate, moving J forward, then I move it back to where the I pointer is. So that means I have 2 loops. There's an outer loop that iterates through the array. Let's use n to mean the length of the array. So inst.length, I'm just going to call that n for short. And so this outer loop could iterate up to n times. It doesn't always iterate n times, but it could. And then I have an inner loop, this do loop here, which could also iterate up to n times. So it looks like the outer loop can iterate n times, the inner loop can iterate n times, so that's n squared, right? Well, sometimes looks can be misleading because algorithms can be more sophisticated than that. The important thing to notice about this algorithm is that every time you do an iteration of the inner loop, I increases. So we always manage to move one of the indices forward. Oh, I'm sorry, I got my indices backwards here. J is this one here, and I is this one out here. So I is going to advance every single time I look at an element of the array, or iterate the inner loop. And the inner and outer loops both always quit when I is equal to n. So I can only do I++ n times before both those loops are going to stop because their condition for stopping has been achieved. And so that means the reality is that this line in the inner loop can only execute n times before we're done. So this isn't an n squared loop after all, even though it looks like one. The running time of this is never more than n. Also, the running time is never less than n because you always get, you don't quit until I reaches the end of the array. So you do have to do I++ n times. So this is an example of a misleading looking algorithm. At first it looks like it runs an n squared time, but it really runs an n time. Any questions about that? Unfortunately, one of the things we learned from this is that there is not a mechanical formula by which you can always figure out the running time of an algorithm. You actually have to think about the algorithm, what it's doing, how it works, to really understand what its running time might be in the worst case. And this is an inherent problem that can't be fixed. And when I say that, I mean we can prove mathematically that no one will ever write a program that can analyze the worst case running time of every algorithm. In fact, there are algorithms that will only run in a certain time if the Riemann hypothesis is true. And the Riemann hypothesis is the most important unsolved question in mathematics. So algorithms can be really crazy about what their running times are, and sometimes you just can't analyze them at all. Another piece of asymptotic analysis that's important to know is that sometimes you have more than one kind of input to an algorithm, and the running time depends on more than one parameter. It's not just one input size, it's several input sizes. And so to give you an example of that, suppose you want to write a matchmaking program. Something like Match.com, where you've got M men and W women, and you want to figure out which ones are the best matches, or how good each match would be. Again, I'm going to stick with the obvious simple algorithm here, which is we're going to go through all the men and all the women and compare every possible pair and test them for compatibility. I am assuming that the record that describes a person has constant size and that you can do the compatibility test in constant time. So in that case, so now the running time of this algorithm, I'm going to write it TWM. That means the worst case running time is a function of two variables, the number of women and the number of men. And for this algorithm, it's more or less obvious that that running time is W times M. It's both order big O of W times M and big omega of W times M, because it doesn't take longer than checking each pair, but you can't do it really faster than that either. So what does that mean? What does the big theta notation mean when you have a function of two variables? Well, formally it means the following. There exists a bunch of constants, C and D and capital W and capital M, such that the following inequalities hold. D times W times M is less than or equal to the running time, which is less than or equal to C times WM. And that is true for every sufficiently large W and M. So, in other words, if the variable little w is greater than or equal to capital W, and the variable little m is greater than or equal to big M. So this just means you choose some threshold for the number of women and the number of men your algorithm has to process in order for the asymptotics to start looking right. And of course, these two inequalities, the right inequality is what gives you the big O, and the left inequality is what gives you the big omega, and when you put them together, that's what gives you the big theta here. Now, there's something I want to emphasize. It's not just that the running time is in big omega of W of M, but it's also that the running time is not in big O of W squared, and it's not in big O of M squared, and it's not in big omega of either of those two things. And the reason why none of these statements is true is because every one of them is precluded either by choosing way more men than women or by choosing way more women than men. So big omega of Wm is not in big omega of M squared or big omega of W squared, and M squared is not in big theta of Wm, and you just can't compare them. They're fundamentally different functions. And this is something that you have to deal with whenever you have functions of two variables, is that you can't compare Wm with W squared because you don't know that there won't be way more men than women, and you don't know that there won't be way more women than men. So you have to include both of them if your running time involves both of them. And so to give an example there, suppose we decide to expand our matchmaking service so that not only does it match men with women, but it also matches up women's volleyball teams. So for every set of 6 women in our sample set, we're going to put them together and do a constant time compatibility test to see if that's a good volleyball team and rank the best ones. Then now the running time is in big theta of Wm plus W to the 6th power. Because you've got big theta of W to the 6th different women's volleyball teams you can form from a set of W women. And these two terms are not comparable. You can't eliminate one of them by saying that the other one always asymptotically dominates it, because it doesn't. Either one could be asymptotically dominant depending on how big W and M are compared to each other. Any questions about that? Yeah, in the back. Sorry, O big O of what? So you're saying if I have an algorithm whose running time is W of M, is it correct to say that's in big O of W? Is that what you're asking? Louder? If M is held constant, then M is not a variable anymore, and we're not doing the same thing anymore. So if I talk about asymptotic notation where the running time is a function of W and M, then W and M are not constants by definition. If I want M to be a constant, then I don't say T as a function of W and M, I just say T as a function of W. And that's a whole different thing. So the first thing you have to do is you have to say what your scenario is, what your variables are, and once you've decided that, you don't treat your variables as constants. Yes, red shirt, please. To draw a graph of this when there's more than one variable. Nothing comes to mind. Do you have a particular kind of graph in mind? Or you mean, you're talking about, you mean this kind of graph, I guess. So what you need is something that can plot a three-dimensional graph, which I don't think I can do by hand very well. If you have Mathematica, it does that really well. But W times M is the contour lines would look like this. These are lines of W times M being constant. So as you get further and further out on these lines, Wm gets bigger and bigger. That's the best I can do. Mm-hmm. Yes. A fine question. So if you have something like big theta of Wm plus, was it Wm squared was your example? Yeah, okay. This is different. This is a case where one term does dominate the other. Since we're interested in the behavior as m goes to infinity, or at least the behavior as m is not 0, this term always is the dominant term out of these two. And so you can write this as big theta of Wm squared and leave the Wm term out. Because as long as m is greater than or equal to 1, that second term is bigger than that first term. And that would still be true even if this was like 1 over 100 here. That would still be the dominant term because the constants don't matter. And likewise, if you have something like Wm plus m, then once again, the m term does not dominate, and the Wm term does dominate. And there are really tricky situations, like this is not obvious, but you can prove that if you have m squared plus Wm plus w squared, you can drop the middle term and that doesn't change anything, because either w is bigger than m or m is bigger than w, and in either case, the middle term does not dominate. So there are places where you can drop a term, but you do have to be very careful about it. All right. I want to do a more interesting version of multivariable. Here's a problem where I have an array that contains the titles of all the albums in my music collection, and they are sorted. So they're sorted by the title. My goal is to find all the albums whose titles begin with the best of. So you'll get the beast of. The best of Fleetwood Mac, the best of Madonna, whatever. And let's suppose that there are k such albums. So that gives me a second variable that's different from n. N is the total size of my record collection. K is the subset of that that begins with the best of. And my algorithm is, first I do a binary search and find one match. Now, binary search will find me a match, and I don't care which match I find first, just any album that starts with the best of. Once I've found one, I can find the others by just walking through the list because I know they're all next to each other. So I only have to do one binary search. Then, because all the albums are clustered together, I can find them in k time. So, the worst case running time is in big theta of, well, binary search in the worst case is going to take log of n time, where n is the total number of albums. But once I've found one match, the best of album, I can find the others just by walking locally in the array, and that only takes k time if k is the number of albums that I'm going to output. But what's interesting here is that these two terms, log n and k, can't necessarily be compared with each other asymptotically. And the reason why is because k could be as large as n, or it could be as small as 0. And what that means is there are times when the k term dominates the log n term, and there are times when the log n term dominates the k term. You don't know which one's going to be bigger for any particular case. And so there is no simpler expression than this. You can't drop one of those terms. And this is an algorithm that we call output sensitive. An output sensitive algorithm is one whose performance depends partly on the size of the output and not just the size of the input. And by the way, because binary search sometimes gets lucky and finds a match right away, the best case running time is in theta of 1 plus k. The reason why saying 1 plus k is because sometimes k is 0, and I want an expression that's correct even when k is 0. Any questions about that? All right, see you all Wednesday.